Hello everyone, I am Kausal Patel from Mechanical Engineering Department at Mahatma Gandhi Institute of Technical Education and Research Center, Navsari. In this video, we are going to determine the equation of motion for a simple spring mass system using energy method and Rayleigh's method. These both methods are based on law of conservation of energy. In previous video, we have derived the equation of motion for a simple spring mass system using FBD method, or we can say equilibrium method, in which we have used D'Alembert's principle. Okay, now in this video, we are going to derive the same equation of motion for simple spring mass system using energy method. Okay, so energy method, that is one of the method which is based on law of conservation of energy, and we already know what is law of conservation of energy. That is, energy can neither be created nor be destroyed, but it can be only converted from one form to another form. Okay, so we are going to use this law to find out equation of motion for simple spring mass system. Okay, so as the name suggests, in energy method we are going to concentrate on particular type of energy which is involved during vibration. Okay, for undamped free vibration of simple spring mass system, we already know that it is concerned with the two types of energy, that is kinetic energy and potential energy. Okay, so kinetic energy is converted into potential energy and potential energy is converted into kinetic energy during the vibration. Okay, so this cycle continues during vibration. So here vibration is undamped free vibration. Undamped vibration means there is no damping provided externally to reduce the amplitude of vibration or to resist the vibratory motion. Okay, so it means there is no energy loss during the cycle of vibration. Okay, generally this kind of energy losses, it is due to friction and it is in the form of heat. Okay, kinetic energy, it is due to the motion of mass or inertia that we already know, and it is depending on the velocity of that mass. Okay, then potential energy, it consists of two parts. First one, that is gravitational potential energy. It is due to the position of a body. For example, if a body is lifted to certain elevation of height, then that work is stored in the form of potential energy, and that potential energy, it depends on gravitational acceleration and the elevated height. So in this case, we already know the equation of potential energy, and that is mgh. Okay, so it depends on mass, gravitational acceleration and height. Okay, while second types of potential energy, that is strain energy. Okay, and it is due to the elastic deformation of a body. Okay, so whenever a body is displaced or deformed within its elastic limit by applying external forces, then that work is stored in the form of strain energy. Okay, so that work is done against elastic constraint provided by that body. Okay, so energy stores due to the elastic property of body, okay, which is strain energy. Okay, so in present case of simple spring mass system, the potential energy, it is in the form of strain energy. So we need to find out strain energy. While gravitational potential energy, it plays a role in simple pendulum that we are going to discuss later. Okay, so we already know the equation of kinetic energy, that is 1/2 mv square. Here v, that is nothing but x dot. X dot, that is first order differential of linear displacement with respect to time, and that is nothing but the velocity. Okay, so we can get the kinetic energy from this equation. Okay, now potential energy, it is in the form of strain energy, which is stored in the spring. Okay, so to find out strain energy, we need to study the force versus deflection diagram. Okay, here we have assumed that spring behaves linearly, so that's why the force versus displacement diagram, that is linear. Okay, now here force is applied to get certain deflection within elastic limit. Okay, whenever that force is removed, then it would try to return to its initial position, or we can say mean position. Okay, so whenever a body is deflected through certain distance, then the total strain energy stored in that body due to elasticity, which can be given by the finding out the area below this curve. So it would represent strain energy of a spring. So here the area under the curve, which is triangle, and we know the equation of a triangle, that is 1/2 base into height. So here base is x and height would be F, which is spring force. So we already know spring force, that is nothing but K into X. Okay, so finally strain energy could be given by this equation, 1/2 height into base. Okay, here height, that is spring force, and base, that is X. Now spring force, instead of spring force we can write down K into X, stiffness into linear deflection. So ultimately strain energy would be given by 1/2 kx square. Now as per the law of conservation of energy, total energy would remains constant. There is only a conversion of energy from one form to another form. There is no energy loss, because we have assumed that the vibration is undamped, right? So here total energy, that is nothing but the summation of kinetic energy plus potential energy, and it remains constant. Okay, now by taking differentiation with respect to time, so d by dt of kinetic energy plus potential energy, that would be equal to d by dt of constant, that is nothing but 0. We already know that the differential of a constant term, that is 0. Okay, now we are going to differentiate this equation. So here 1/2 m and 1/2 k, that is constant. We need to differentiate x dot square and x square with respect to time. So here 1/2 m constant, differentiation of x dot square, that is twice x dot, into differentiation of x dot, that is x double dot. So the differentiation of x dot square would be twice time x dot into x double dot plus 1/2 k constant. Okay, now differentiation of x square, that is twice x, into differentiation of x, that is x dot. Okay, so the differentiation of x square would be twice x into x dot, okay, is equal to 0. So here equation could be simplified as mx double dot plus kx is equal to 0. Now this equation could be written as x double dot plus k by m times x is equal to 0. This is nothing but the equation of motion for simple spring mass system, which we have previously determined using FBD method. Okay, now by comparing this equation of motion of simple spring mass system with the equation of motion of simple harmonic motion, we can get natural frequency omega n as in square root of k by m radian per second. Now frequency in hertz, that is nothing but omega n divided by twice pi, so it would be given by 1 by twice pi in square root of k by m hertz. and periodic time, that is nothing but the reciprocal of frequency in hertz. So it can be given by twice pi in square root of m by k second. Okay, so in energy method we have used the law of conservation of energy. Okay, now there is another method which also based on law of conservation of energy. So this method is also based on law of conservation of energy, that is nothing but total energy remains constant. Here we are going to consider energy at different positions. Okay, a system at mean position and the system at extreme position, upper extreme or lower extreme. Okay, so total energy would remains constant as there is no energy loss. So total energy at mean position, that would be equal to total energy at extreme positions, right? So let energy at mean position be represented by subscript 1 and energies at extreme positions that could be represented as subscript 2. Okay, so total energy, that is nothing but the summation of kinetic energy plus potential energy. So kinetic energy plus potential energy at mean position, that would be equal to kinetic energy plus potential energy at extreme position. But we already know that the kinetic energy at extreme positions would be 0 and it gets maximum at mean position, while potential energy, it gets maximum at extreme positions while it is 0 at mean position. Okay, so as kinetic energy, it depends on velocity. We already know that at mean position the system would have maximum velocity. So at mean position kinetic energy would be maximum, while kinetic energy at extreme position, that would be 0 because at extreme position velocity of system gets 0. Okay, same way potential energy, in case of simple spring mass system, it is strain energy. Okay, so strain energy, it depends on the displacement from the mean position. If displacement from the mean position is maximum, then strain energy would also maximum. Okay, so we already know that at mean position the displacement from mean position would be 0, so potential energy would be 0, right? So potential energy would get maximum when it is at extreme positions, upper extreme or lower extreme during longitudinal vibration. Okay, so from this relation kinetic energy at mean position would be maximum. Okay, potential energy at mean position, that would be 0. Here kinetic energy at extreme positions, that would be 0, while potential energy at extreme position, that would get maximum. So ultimately we can get the relationship like this: maximum kinetic energy would be equal to maximum potential energy. So that is the statement of Lord Rayleigh. According to Lord Rayleigh, the maximum kinetic energy at the mean position is equal to the maximum potential energy at the extreme position. Okay, now we already know the equations of kinetic energy and potential energy or strain energy. Okay, so kinetic energy, that is 1/2 mv square, 1/2 m x dot square, while strain energy, that is 1/2 kx square. So here 1/2 m and 1/2 k, that is constant. We need to find out displacement x and velocity x dot to get the equation of kinetic energy and potential energy. So here we know that the vibration is in the form of simple harmonic motion, and we already have the equation of displacement for simple harmonic motion, and it is x is equal to capital X sine omega t. So from this equation we can get displacement at any instant of time. Okay, so from this equation we can easily get the maximum value of displacement from the mean position, and that would be equal to the amplitude capital X. Okay, so small x would get maximum when this term sine omega n into t gets maximum. It means it becomes 1, then x would be equal to capital X, that is the maximum displacement of a system. Okay, now using this equation we can get velocity by simply differentiating with respect to time. Okay, so by taking first order differential we can get x dot is equal to omega n x cos omega n t. Okay, so from the equation of velocity of a body x dot, we can see that it would get maximum when this cos term cos omega n into t gets maximum. It means maximum value of velocity x dot, that would be equal to omega n into x. So by putting these values of maximum velocity and maximum displacement in the equation of kinetic energy and potential energy, we can get the maximum kinetic energy and maximum potential energy. So by substituting the value of maximum velocity in the equation of the kinetic energy, we can get the maximum kinetic energy as 1/2 m omega n square into x square, while potential energy, that would be equal to 1/2 k into x square. Here capital X, that is the maximum displacement, and it is nothing but the amplitude of vibration. Now we have the statement maximum kinetic energy at mean position would be equal to maximum potential energy at extreme positions. So 1/2 m omega n square x square is equal to 1/2 k x square. Okay, so from this relation we can get omega n square is equal to k by m. So ultimately we have got the equation of natural frequency omega n is equal to in square root of k by m radian per second, which is the same equation which we have previously determined. Okay, now frequency in hertz could be given by this equation and periodic time could be given by this equation. Okay, so same equations we have derived by using Rayleigh's method.